Pick up on this video where we left off yesterday, and I'm going to show you how to do the trapezoid sum to get us started. Okay, so we talked about yesterday that to get the average temperature of this wire, we need to integrate from, where were we? So 0 to 8, we want to do 0 to 8, we want to do T of X, dx, and we want that over 8 minus 0. That gave me the average temperature. That's where we ended up yesterday when we finished up. So now we want to use the trapezoidal sum to figure out what the integral from 0 to 8 of T of X dx is to get our estimate for our average. Okay? So I'm going to go back and plot this one just like I did with the rectangle because it's going to be tough to visualize if we don't plot it. So let's go ahead and plot it. Alright, so this is going to be my units here, and then centimeters is going to be my units there, and we're going from 0 to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So 0 to 8 centimeters, and my y value goes from 55 to 100. So we'll say that is 55, and we'll say that is 100. Okay, so at 0, our point would be at 100. At 1, we're looking at 93, somewhere in there. At 5, 1, 2, 3, 4, 5, we're looking at 70, which would be somewhere in there. At 6, we're looking at 62, 1, 2, 3, 4, 5, 6, so somewhere just a little bit below that. And then at 8, we are at 55. So we'll make that. Okay? Now, at this point, if we were doing a right or left Riemann sum, then we're going to go up on the right, or we're going to go up on the left, and then we're going to make our rectangle. But if we're doing a trapezoid, we're going to go up on both sides. Okay, so in my first section here, I'm going to go up here, I'm going to go up there, and then I'm going to connect those two pieces. Okay, and I have now created the trapezoid that it was talking about. I have now created the trapezoid. It just looks a little bit different than what you're used to. This is kind of a trapezoid that's on its side. You're used to seeing this trapezoid in that shape. So if I take this and then turn it, I'm in that shape. Okay? And if you remember, the area formula for a trapezoid is 1/2 my height, and then I add my bases together. Okay, so if I'm looking at this, my height would be that piece, and then I would have base 1, and I would have base 2. So if I take this and then move it over here and stand it back up, that means this piece right here is my H, this piece right here is my B1, and then this piece right here is my B2. Okay, so that means instead of just using the right or just using the left value, I need to use both values to get B1 and B2. Okay? And then I plug those in here. My height is going to be however much this is. I plug that in there, and then that gives me the area for this piece. Okay? So, now that I have this, I'm going to go ahead and draw the rest of them. 1, 2, 3, 4, 5. So I go here, and then over. I go here, and then over. And I go here and then over. So I've got 1, 2, 3, 4 different trapezoids. Okay? But now that I have this, I'm going to ignore what's going on here and get all of my information from up here. Okay? Because all I need is how far am I moving, which comes from the top, 0 to 1, 1 to 5, 5 to 6, 6 to 8, just like we did on the rectangles. And then on the rectangles, we chose one of the two sides. If I'm doing trapezoid, I need both sides. So I put both of those sides together, and then I've got the 1/2. Okay? So my first one right here, the distance here is 1. I put those two together, I get 193. So that means the area of this first section right here is 1/2. 1 is how far I went here, and then put those two together, I get 193. So this gives me the area of my first trapezoid. Second trapezoid. How far? I'm 4. Don't forget your 1/2 though. So 1/2, we are 4 apart, and then I need to add these two together, so that's going to be 163. All right, next one, how far? They are 1, so I need the 1/2. I need the 1. I add these two together, that's 132. And then the last one, how far apart are they? They're 2. Don't forget your 1/2. I've got my 2. I add those two together, that gives me 117. And then I multiply these and add them all up. But if you notice, each one of these has a 1/2. So I would take that 1/2, multiply, 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 add those, and then multiply by a 1/2. So let me do that real quick on my calculator. And I'll be back to you in just a second. So I've got 193 plus 163 times 4. Plus 132 plus 2 times 117, that's 234. And then I multiply by 1/2, and that gives me 605.5 if I did it correctly. Now remember, so all of this together right here, I ended up with 605.5. So let me bring you over here. Now remember, all of this is part of the 0 to 8 integral of t of x dx, and then over 8 minus 0. So what I just figured out was just this top part. So just this top part is 605.5. The bottom is 8. So I need to divide 605.5 divided by 8. And I end up with 75.687. So 75.687. And then we talked about yesterday that my units right there should be degrees Celsius, because we're talking about average temperature. My units for an average temperature should be degrees Celsius. Now, we should make sure that our answer makes sense. So if I look over here, and I look at all my degree measurements, 100, 93, 70, 62, 55, and I compare that to what I have as my average temperature, does it make sense that my average temperature could be 75.687 degrees Celsius? Okay, and notice 75 fits in there in those numbers, so that means my average temperature, my estimate, is fairly good. Okay, so that's what's going on that problem. That's how you find Riemann sums with trapezoid or trapezoidal sums. Okay, again, I need the distance here, which is the distance from here to here, here to here, here to here, here to here. Instead of using one or the other, we're going to use both, and I've got to add them up, and then don't forget the 1/2. So that's how you use the trapezoid sum. So that gets you caught up to date with the trapezoid sum. So there's that. So now let's move on to the new stuff. Okay, so like I told you yesterday, we want to go back and look at the parts of an integral and look at their names. So that's what we have here. So this right here is our integral sign. And if you notice, this integral sign looks like an S. Because if you remember, when we're doing Riemann sums, I'm finding a bunch of areas and then doing what with them? I'm adding them up, which means I'm finding a sum. So that's why this figure right here looks like an S. Okay? Then we talked about we have A and B right here. Those are our limits of integration. So this is our lower. It's on the bottom. It's our lower. This is our upper. Okay? The function that's inside is called the integrand. So our function inside is called the integrand. And then our variable of integration is whatever variable is right here. Okay? That's one of the things we have right here. We need this here so that we know when we integrate, we're dealing with this. Because we might be integrating something that doesn't have a number. So if I do that, I've got to have a variable here that tells me what variable I need to end up with. Okay. When I work one of these out, when I work a definite integral out, I have evaluated the integral. Okay. So there's a little bit on that. So let's get to this piece right here. All right. So we're going to work these three right now, and then I'm going to leave these three for you when you do your assignment over this problem. So we're going to work this, and it's tough to see right here. So I'm going to move over here to the left and rewrite them. All right, so the first one is the integral from -2 to 1 of 5 dx. Okay? If you remember yesterday, I told you there were two main takeaways you needed to get from yesterday, and those two are that a definite integral represents the change in the function above, and it also represents the area under the curve. Okay? So when we're doing these problems today, I'm interested in the area under the curve. Okay? And the curve we're talking about is this curve. So I need to know, what does the curve 5 look like? Okay? And it's one of those things where it's so simple you may get hung up on it. But the curve 5 is nothing more than going up to the y value of 5 and then drawing a horizontal line. That's all this curve is. Okay? And I'm interested in from -2 to 1. So from -2 to 1, I'm interested in this. And as we just said, a definite integral, one of the explanations is it represents the area under the curve. So I'm interested in all of this area, which is nothing more than a rectangle. Okay? So I need to know how wide it is, which is 3, and how tall it is, which is 5. When I multiply those two together, that tells me this is 15. Pretty simple. So we go to the next one. I have the integral from 0 to 3 of -160 dt. So I want to work this out. Again, that right there, if I were to graph it, so here's my x-axis, -160 is going to be down here somewhere. So there's -160. I'm interested from 0 to 3, 1, 2, 3. So that means I'm interested in that box right there. So this distance is 3, this distance is -160. I multiply that together, and that gives me -480. Okay? Notice that my answer here was negative, and notice, where is my area? My area is below the x-axis. If you have area below the x-axis, that area is going to be negative. On the previous problem, my area was above the x-axis, so that area is going to be positive. So area above is positive, area below is negative. All right, next one. Integral from -2.1 to 3.4. And we're integrating 0.5 ds. This time I'm not going to draw it. We should be able to figure it out. I need to know how far is it from here to there, and then multiply times this. So from here to there, that's going to be 5.5, and then multiply it by 5. So 5.5 times 0.5. And that gives me 2.75. So this definite integral is 2.75. There it is. All right. All right, next thing we want to do is talk about some of the properties of definite integrals. So let me scroll. Nope, we're going to have to do that over here because I don't have it on a slide. All right, so let's say I have the integral from a to b of f of x dx, and it is equal to 3. Whatever that function is, the area under the curve between a and b is equal to 3. It doesn't matter what that function is. This is just for purposes so you can see some of our properties. So if that's equal to that, my next question would be, what do you think it would be if I did 2 f of x dx, and I wanted to know, what was that equal to? Okay? Well, we should realize that that 2 is nothing more than a coefficient, so that means all I would have to do is take that 2 times that 3, and I would end up with that one would be 6. So if you've got a coefficient, you can just take that coefficient times the integral of whatever that is, and then you get your answer. Okay? Another thing that's one of those that's so simple you might get hung up on it is this problem. Notice I'm doing the integral from a to a of f of x dx. Okay? But notice a to a. I didn't go anywhere. Okay? So if I were drawing it, or if I drew it, I would notice that the distance from here to here is 0, and then 0 times anything else is always going to be 0. So my property here is, if this and this match, no matter, regardless of what's in here, my answer will always be 0 on that integral. Okay? Alright, so notice this one is the integral from a to b of f of x dx equals 3. What do you think happens if I do b to a of f of x dx? So I reversed it. Instead of from a to b, I went from b to a. Okay? Hopefully you're thinking, well, if I've reversed it, then all I have to do is change the sign. So if this one's positive, then this one's going to be negative. If it started out negative, then this one's going to be positive. So whenever you reverse the limits, all you're doing is changing the sign. Pretty simple. All right, next one. I'm going to give us a new function. Let's say I have the integral from 1 to 3 of h of x dx, and that equals 4. I've got another integral from 3 to 7 of h of x dx, and that one equals 2. My question to you is, what would the integral from 1 to 7 of h of x dx be? Okay? And again, this goes back to, what does this represent? Again, that is area under the curve from 1 to 3. So the area under this curve from 1 to 3 is 4. The area under this curve from 3 to 7 is 2. So now it's wanting to know, what would the area be if I went from 1 all the way to 7? So if I go from 1 all the way to 7, what would it be? So this one's 1 to 3. This one's 3 to 7. So hopefully you're on board with saying, well, all I have to do is add these two together, and I get 6. So let me give you a graphical representation of this, if I can talk. All right, so the first one is 1 to 3. So 1 to 3 right there, and my integral is going to be whatever my function is. I don't care what it looks like. Okay, that area right there is equal to 4. Okay, and then we go from 3 to 7. 4, 5, 6, 7. And let's say we're down here. Okay, so let's say this area in here is 2. So from 1 to 3, my area is 4. From 3 to 7, my area is 2. All this problem is asking is, well, what's my area from 1 to 7 have to be? And hopefully you can see, well, if this is 4 and this is 2, then all I have to do is add those two together, and I get my area of 6. Okay? The key is, so if I go 1 to 3, and then the next one is 3 to 7, the key is that these two things have to match. If these two things match, then I can put these two integrals together. If these two numbers don't match, then I can't put these integrals together. So we just got to make sure that these match, because if they don't match, then that means there's a gap in here, and I can't add my areas. All right, one more of these properties. If I have the integral from 0 to 5 of f of x, some function plus or minus some other function of d of x, that means I can, this property says that I can take it and I can separate these two. So I can separate these two into two separate functions. That's all this property says. So let me give you something that might be more realistic to you and you might be able to buy. So let's say I have this function right here. Okay? and I can separate this. So I can think of x squared as f of x. I can think of 3 as g of x. So that means I can separate this into 0 to 5 x squared dx plus the integral from 0 to 5 3 dx. Okay? And as you noticed earlier today, this is a problem that we did earlier today when we were back on here. All I need here is the distance times 3. So I already know that that's 15, and then we'll figure out how to do this a little bit down the road. But I can take this and I can separate it into different chunks and then work each piece separately if I want to. That's all this function, or all this property tells me. All right, we are back to the board, and let's scroll. All right, so right here, hopefully you can read it. Integral from -1 to 1 of f of x dx equals 5. So the area under this thing from here to here is 5. The area under this thing from 1 to 4 is -2. And then the area from -1 to 1 under this thing is 7. Okay, notice this is F, and this is H. Okay, so keep that in mind. So it's wanting to know, if I have these up here, can I work these 6 down here underneath? Okay, so on this one, find each of the following integrals if possible, because some of these aren't going to be possible. You'll see in just a second. So can I find 4 to 1? Well, we just talked about that a second ago. This has 1 to 4. And this one wants 4 to 1, so that means all I have to do is take this answer and then change the sign. So that means this one is equal to 2. Let me change this. Okay, so this is equal to 2. The next one, -1 to 4. Okay, this one goes -1 to 1, so the area from -1 to 1 is 5. This one, the area from 1 to 4 is -2. I want the area from -1 to 4, okay? And as I just showed you over here, if I want to put 2 integrals together, then that means that piece and that piece have to be the same. If they are the same, then all I have to do is add their numbers. So since they are the same, all I have to do is put those 2 together, and we end up with 3. So that integral would be 3, okay? These 2 have to match, and then these 2 have to be where you're going. So notice I have a -1, which is right here. I have a 4, which is right there. And then those 2 match. If that happens, then I can just put these values together. All right, next one. We're going -1 to 1 of 2 times f of x, and then 3 times h of x. So this goes back to that one where we can, our property where we can separate. Okay, so let's look at this piece first, just this piece. -1 to 1. Well, here's -1 to 1, and it's equal to 5. But we've got that coefficient, just like we talked about on that property a second ago. All I have to do is go my coefficient times this value. So I'm going to get a 10 out of that piece. And then over here on this piece, do the same thing. -1 to 1, -1 to 1. I've got a coefficient of 3. So 3 times 7 means that this piece is 21. Put those 2 together, and we work that out as 31. All right, next one. 0 to 1 of f of x. But hopefully you're noticing there's a problem here. In any of my integrals that deal with f, there's f. Notice that there is no 0 anywhere. Okay? The values that are right here have to show up here in order to work it out. So this one right here is not possible, because I have nothing up here in f, nothing up there that has a 0 on it, therefore not possible. Same thing on this one. -2 to 2 of h of x. Here's the only thing with h. -1 and 1 does not match up with -2 and 2, so this one is also not possible. We go to the next one, -1 to 4 of f of x. I can do -1 to 4 because I got a -1 here and I've got a 4 there, so I can do that one. But it also wants h of x from -1 to 4. I can't do that because h of x only has negative 1 to 1, so that means this one is also not possible. So there are evaluating some definite integrals using the properties. That's what's going on there. Next problem. All right, again, they're going to give me some definite integrals up here, and then they're going to want me to use them to solve what's going on here. So this one is 2 to 2. This one should be easy because we have the property that if this and this, these two are the same, regardless of what's inside, that's going to be 0. Next one, 5 to 1 of g. Here's g. This g says 1 to 5. I want 5 to 1, so all I have to do is change the sign, and I get negative 8. So that one's negative 8. Here, 1 to 2, 3 times f of x. Here's 1 to 2 of f of x. This has a 3. This one doesn't. So I just multiply this by 3. I get negative 12. All right, 2 to 5 of f of x. So here's f of x. Here's f of x. I have a 5, and I have a 2. Okay? I have to put these two together. But the problem is, right now, I do not have a match right here, and I need 2 to be down here in the corner. Because if I'm going from 2 to 5, I need to have 2 here, I need to have 5 there, I need to have a 1 here, and I need to have a 1 here. So hopefully you're thinking and saying, well, all I have to do is switch this around, and then I've got what I want. So if I flip that around, I get 2 to 1 of f of x dx, and if I flip that around, it's going to go from negative 4 to 4. Now I've got what I want. I've got my match here. I'm going from 2 to 5, so all I have to do now is add those together, and this is going to be 10. Okay? So make sure this is the bottom left, this is the upper right, and then make sure the bottom and the top match up. If you have that, then you can put them together. Here, 1 to 5 of f of x minus g of x. So here's 1 to 5, here's 1 to 5, I have f minus g, so that's going to be 6 minus 8, which gives me the negative 2. Next one, 1 to 5, 4 times f of x minus g of x, so this is the same thing as this one, except I've got 4 times f. So I need to take a 4 in here, 6 times 4 gives me 24, 24 minus 8 gives me 16. So my answer to that one would be 16. Hopefully you're finding those to be somewhat doable. All right, so next one, we have 1 to 2 of f of x equals 5. We want to use that information to figure this out right here. So 1 to 2 of f of x equals 5. The only thing that's happened on this one is that they changed the variable. That really doesn't matter to me. So 1 to 2 is still going to be 1 to 2, so that means this one's going to be 5. On this one, 1 to 2 square root of 3 times f of z. So the only thing different on this one is I have a z and I have a square root. So this is a coefficient. I just need to multiply. I end up with the square root of 3 times 5. That looks funky. Let's change that to that. All right. Then we've got 2 to 1 instead of 1 to 2. So all I have to do is change my 5 to a negative 5. Then my last one, 1 to 2 of a negative f of x. That's going to end up giving me the same answer as this one. So there's that. All right, next one, we have negative 3 to 0, and that gives me 2. Negative 3 to 0, and that gives me 2. So the first one just switches it. So all I have to do is change my sign, which gives me negative square root of 2. On the next one, we're doing negative 3 to 0, which matches. The only thing different about this is the variable. That doesn't mean anything to me. So that's going to be the square root of 2. Next one, negative 3 to 0 of a negative g of x. So that's just going to be a negative square root of 2. And then my last one, negative 3 to 0 of g over the square root of 2. That square root of 2 is nothing more than a coefficient. It would be the same as if I had this. So that's nothing more than a coefficient. So all I have to do is take this times my value. So that's 1 over the square root of 2 times the square root of 2, which gives me 1. So that would be 1. All right, now this next one is a problem that I usually like you guys to struggle with and try to figure it out on your own. So if you're up for struggling and trying to figure it out on your own, I would recommend you press pause on the video, spend a couple minutes on it, and then come back and see if you can get the answer. So if you're up for that, go ahead and press pause, try to work on it, and then come back and let's see how you did. All right, so it says if a to b of f of x dx equals a plus 2b, so this equals that, then what does that equal, is what it's wanting to know. So hopefully, the first thing you realize you needed to do is, since I have something plus something else, hopefully you realize that you needed to separate that into two different integrals. So my first integral is a to b of f of x dx, and then my second integral would just be the 3. Would just be that. Okay? Well, this right here is what they gave me. So I can replace this with a plus 2b. So I know this right here is a plus 2b. Now all I have to do is figure out what that is. Okay? Well, this goes back to the very first thing we did today whenever we're dealing with the number that's right here. Okay? So I've got 3. And then we're going from A to B. Doesn't matter where A to B is, if that's A and that's B. So all I need is that area. So I need the distance between here and here times how tall it is. So to get this distance, I'm just going to subtract B minus A, and then this distance is 3. So if I multiply, I get 3 times B minus A. I distribute that. I get 3b minus 3a, and then I combine that with what I already had. So I've got an a, I've got a negative 3a, so that's a negative 2a. I've got a 2b and a 3b, which gives me a 5b. So that means we ended up with negative 2a plus 5b. And my answer is going to be D. If you got that right, you're doing pretty good. If you didn't get it right, that's fine. That's one of the tougher problems we do today. All right, a couple more quick problems, and then you're done. All right, so they're giving me a function, and they give me a shaded area in here, and what they want me to do is they want me to write a definite integral that represents that area. Because again, one of the things I told you a definite integral represents is the area under the curve. So I want a definite integral that represents that area under the curve. So all I've got to do is integral from where to where. Okay, we're just looking at this right here from 0 to 2. So I put 0 to 2 in there, and then all I need is, what is this function? Well, that function is 6 minus 3x. And then put your dx behind it because I'm dealing with x's. Okay? That's all at once. So on the next one, this is what I'm looking at. We're going from 0 to 2. And then my function is this right here, which is the x squared. So then I put the x squared in there, and I put the dx. All right, one more. All right, so this one is g of y equals y cubed. So this is what we look like. Now, hopefully you're noticing that this one is different. This one is in terms of y. The other two were in terms of x. So if I am in terms of y, as this one is, instead of putting x values here and here, I need to put y values here and here. So I need to be looking at the y values I'm using. So my y value is going to start with 0. And then my highest y value is going to be 2. So I'm going to do 0 to 2. I don't know why I wrote a 0. So 0 to 2. And then all I need is my integral, or whatever my function is, which is y cubed. And this time, since I'm dealing with y, instead of putting dx behind it, I need to put dy. And there it is, nothing to it. So, if you're in terms of y, make sure you use the y values for your integral, and make sure you put dy behind it. If you're in terms of x, then you want to use x values. Okay, if this one was in terms of x, I would have done 0 to 8 instead of 0 to 2. But it's in terms of y, so that's why I did 0 to 2. So if it's y, I need dy and I need y values. If it's x, I need dx and I need x values. Okay? So there's a quick rundown of properties of definite integrals, and then using those properties to evaluate definite integrals. That's what we've got there. If you need to, hopefully you're going to pause and rewind as you went through that. And I haven't decided what I wanted to do for Wednesday yet. I may give you another video on Wednesday. No, sorry. I haven't decided what I want to do on Thursday yet. This is the video for Wednesday, today, your day. And then tomorrow, Thursday, I haven't decided yet. Depends on what the stuff is. If the material I'm covering on Thursday isn't too difficult, I'll probably give you another video. If it's difficult, then I'll probably just give you some more work, practice on this stuff. Anyways, there it is. I hope you guys have a good day. We'll see you on Friday.